Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem.
Yo, what's up, chemistry folks? What are we learning today?
Molar mass and ideal gas.
And basically, today we're going to be teaching you the knowledge and the stuff behind the gases in the molar mass.
All right. Molar mass and ideal gas. Woo!
Houston, we don't have a problem. Today we're going to find how to use PV equals nRT to calculate the molar mass of a substance. So the best way to do this is not new. This is not new stuff, but it's going to be a little like connecting things we've already learned. All right, so we know PV equals nRT. We understand that equation. And molar mass. So let's do a little review of molar mass. Molar mass, as you call, is the number of grams divided by the number of moles. So if you know the number of grams of a substance and you know the number of moles, you take the grams and you divide by the moles. Guys, we're going to use PV equals nRT, and the N, of course, is moles. And we're going to have to find the grams in some other way. So you're going to solve for moles. That's going to go here, most likely. And then you'll probably be able to weigh this. This is very useful because it's something that's easily done in an experiment. I can weigh something, find its mass, or determine its mass, if you will. Then I can find its molar mass. I think to understand this best, no question, is to do a problem. So let's say that I have a gas, all right, and I find it by mass displacement or simple weight loss. So let's say I've got a flask, right? In this flask, I put a certain mass of something, all right? Let's say I have some acid in here, some acid. And in that acid, what happens is I add the acid to some chemical, and then a gas is given off. But then I hook it up through a system of pipes, if you will, right, tubes and whatever. And what I do is I put it into, a thing filled with water, and then we collect it up into a tube, and we measure the volume. All right, so the question would be, what would the molar mass of that gas be? So let's give some information. Let's say that this container, the mass when it starts out is 100 grams. Okay, this is before mass, right? And then after, the mass is 99.5 grams. So what's left this reaction vessel is just this gas. So what you can do is if you subtract these two numbers, you would say that the mass of the gas is 0.50 grams. So again, we're trying to find the molar mass. The molar mass is the grams divided by the moles. So this is the gram number, right? This is the number that you're going to put here. To do the moles, you do PV equals nRT. So let's say that I collected, this is the amount of gas that I collected, and it's easy to measure with the device. Let's say the volume is 62 milliliters. I measured at a particular temperature, so I used a thermometer, and I found that this was at 22 degrees Celsius. And let's say that I measured the pressure using a barometer. And let's say the pressure of the day was, shall we say, I don't know, let's say that we lived in Colorado, and the pressure is 610 millimeters of mercury. The question is, what is the molar mass? Well, know that we've got P, T, and V. We're trying to find N. And that N is the N that's going to go here. Of course, we know R is what it is. Now, we do have to do some conversions. If this is in milliliters, I'll say there's 1,000 milliliters in 1 liter. So that's 0.0620 liters. I'm going to have to convert this to atmosphere of pressure. Actually, let me take a moment here. We've got to do something else, is that we have to look up the water vapor pressure of, since this is going to be collected over likely water, right? This is filled with water. Because what's happening is this gas, whatever this mystery gas is that came out of here, there's some of that gas, but what's also happening is there's going to be a very small amount of water. And the way to account for that is with the pressure. So you have to subtract out the water pressure. and I don't know what the water pressure is. There's a table, but I'm going to make up a number because I don't have the table in front of me. But we would look at 22 degrees Celsius, and I'm going to guess that it's probably in about the 20 millimeters. It's not a whole lot, but it's 20 millimeters, meaning that of this pressure, 610 is the mystery gas, and 20 is the other gas. This is an application of Dalton's law of partial pressure. So that becomes, of course, 590. And then I still need that in atmospheres. So I'll say 760 millimeters is equal to 1 atmosphere. Now I'll need to get a calculator on that, which I happen to have right here. So if I take 590 divided by 760, I get 0.776 ATMs. My temperature is in Celsius, so I need to add 22 plus 273, so that's going to be plus 273, that's 295. So now I'm going to plug this into the equation. P is 0.766, that's the P, times the V, 0.0620, equals N times 0.0821, that's R, times 295. Now, again, if you're not remembering this from your algebra class, the way to solve for N is we divide both sides by these two terms here, 0.0821 and 295, 0.0821 and 295. These cancel. So on my calculator, I'm going to type in this number here, 0.766 times 0.062 divided by 0.0821. Watch now. Divided by 295. Do not times them. And I get the grand total, tiny number. That's going to be typical, by the way. N is 0.00196 moles. So that is my moles. This was my grams. So I'm going to take 0.50 grams divided by 0.00196 moles. Get the calculator on that. So 0.5 divided by my previous answer gives me a molar mass of 254 grams per mole. And if we knew some options, we might be able to figure out what our chemical is. So we can find the molar mass of a gas if we have it leave the system, bubble up in there, and kind of bing, kind of boom, we do just mass divided by moles, and moles comes from Mr. Pivnert, and we can solve that problem. Let's do one more example that twists it a little bit. All right, so here's our second example, much more complex, but again, it's connecting things we've already learned. So we've got aluminum reacts with sulfuric acid to produce 110 mils of hydrogen gas, et cetera, et cetera. Now, here we have to always start with a balanced equation. So we are going to take aluminum, that's Al. So make sure you're copying this down, guys. We're going to take aluminum, and we're going to react it with sulfuric acid. So it'll be Al plus H2SO4. And that's going to make, we know, hydrogen gas. We have to figure out the other thing is. You said single replacement reactions. The aluminum is going to get together with the sulfate. So we have to play the charge game. And if you recall, right, going back to our periodic table, is that aluminum is over here in this column right here. And since it's in this column, that's a +3 charge. So I've got to play the +3 charge game. So aluminum is +3, right? And sulfate is SO4, and it's -2. Use a polyion table. You don't know that. 3, 2. I got to get to 6. That'll be plus Al2 parentheses SO4 through. We've got to get to a 6 charge. Okay. Now what do I know? It's not a balanced equation. See, I've got 3 sulfates and 2 aluminums. So I've got 3 sulfates. Let's solve our sulfate problem here. If there's 3 SO4s, I've got to put a 3 in front of here. That gives me then 6 hydrogens. I've got 2 here. To fix that, I put a 3 here. And that gives me, by the way, 2 aluminums, so I have to put a 2 here. All right. Now, what do we know? All right. Let's remember we're trying to find the molar mass of aluminum. This is a weird question because we know the molar mass of aluminum was 27 from the periodic table, but we're going to try and see what it was experimentally. All right. So molar mass of aluminum, right, is going to be 5.3 grams. We know its mass already, divided by so many moles. And we have to find the moles. But what else do we know is we know some information about the hydrogen gas. So for the hydrogen gas, I know the pressure is 77 atmospheres. That's pretty high, but it's a number, okay? we know that the volume is 110 milliliters, right? Right here, right? But remember, it's got to be liters, so that's 0.110 liters. And the temperature is 72 degrees Celsius. So I add 273, that adds up to 345 Kelvin. So now I have P, V, and T, and I can find N. We've played Pivnert games before, so that'll be 77, right? P times V, 0.110 equals N, that's what we're trying to find, times 0.0821 times 345. So now I get my calculator. Now remember, you're going to have to divide both sides by 0.0821 and 345. Those cancel right there, right? Those cancel. So N equals this, so I'll take 77 times 0.11 divided by 0.0821. Is that right? Yes, divided by 345. And I get N to be 0.299 moles. Now this is actually where there is some mistakes that I often see people make. It's 0.299 moles of what? It's moles of hydrogen. You don't need moles of hydrogen over here. You need moles of aluminum. So we have one little simple step. This is the step everyone misses, is that I'll say that the moles of the hydrogen is 3 moles hydrogen. I need to cancel out to 2 moles of aluminum. So what's that come out? So I got 0.299 times 2 divided by 3 gives me 0.199 moles. That's the number that goes here, 0.199 moles. So what does that give me now? So I'll take 5.3 divided by my previous answer, 0.199, and I get, survey says, I get 26.6 grams per mole. Now if you recall, the molar mass of aluminum is, let's pull it up here on the screen. .98 sig figs, that would actually be 27.0. So what I'm going to do is to do the, now remember the percent error, we're going to do percent error. You'll take 26.6 minus 27.0 divided by 27.0 times 100. So 26.6 minus 27.0, I can do that in my head. That would be negative 0.4. So I'm going to take 0.4, negative 0.4, divided by 27 times 100. This would be very low percent error. And I get a 1.48% error. All right, so let's review what I did. Balanced equation. I already knew the mass. I then did Pivnert with my gas. That was the mass right here, right? I did Pivnert with my gas. I solved for N, but N in this case from Pivnert was not the N that went here, because with my balanced equation was not a 1 to 1 to 1 or whatever, it's 2's and 3's. I had to multiply by the mole ratio to get this number, which then went here. I divided and I got the answer. So those are the types of problems you'll see when you combine PV equals nRT and molar mass problems. Houston, we don't have a problem.